gravitation. We'll get right into it, and if you enjoy this content, give us a like and subscribe. So, during Newton's time, it was thought that all the physics that we've been learning so far only applied on Earth, and that these laws didn't work elsewhere in the universe. The rest of the universe had different rules. And one of the great things that Newton contributed was to show us that this is not true, that physical laws on Earth also apply to other places in the universe. And one of those main laws is the force of gravity. So his formula was big G, which is a constant, and that constant is the universal gravitational constant. And it's 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Now, if you think about the Newton meter squared and kilogram squared, that ends up canceling out so that we're left with newtons for the force. The 6.67 times 10 to the minus 11, this number's the same everywhere in the universe, and because it's so small, that indicates to us that gravity is an extremely weak force. In fact, it's the weakest force in the universe. Now, sometimes this formula is written with these absolute value bars, and the reason that's the case is because we really are only going to look at the scalar or the magnitude part of the force, and the reason is because there's not just one force, there always has to be two. For every force, there's an equal and opposite force. So let's say we have two masses, mass 1 and mass 2. Then the force of gravity between these two masses are going to actually be in opposite directions. Mass 1 will experience a force to the right, and mass 2 will experience a force to the left. So what we'll do is when we calculate this force, we'll just leave it as positive, and then if the question asks us what's the direction on M1, we can say to the right, and for M2, we can say to the left. Now, the other crucial thing about this formula is that it says for any two masses. We often think of gravity as something that's acting on Earth, but gravity is the force of attraction between any two masses. This could be a paperclip and a basketball. Everything has a gravitational field as long as it has mass. Okay, so let's look a little bit more closely at this letter R. So if we have mass 1, and we have another mass 2, the definition of R is the distance between the centers. And this has to do with the center of mass specifically. But when it's a circle, it's just the center. So why do we use the letter R? Because R is often associated with radius. And the reason that's the case is because the formula for force of gravity is typically used to find the force of gravity on an object, like let's say a person standing on the planet. Well, from the center of the person to the center of the planet, that is basically the radius. So that's why R is often used. So what does this formula, Fg equals g m1 m2 over r squared, what does that look like? Well, if the masses are constant, and g is a constant, then we can say the force of gravity is directly proportional to 1 over r squared. This is called an inverse square law. So if we were to graph this and we wanted to look at this relationship between the force of gravity and r, that would give us something that looks like this. That is asymptotic. So if we have a problem where we have a ball, and we throw the ball up into the air and we say we want it to go a certain height and then to come back down. In that case, we can use kinematics or we can use conservation of energy. But let's say the question deals with a much larger scale. For example, how fast must this projectile leave the ground to reach 3r above the surface? Now, we're going to be very careful about this later because our formula, Fg equals g m1 m2 over r squared, is always from the center of the planet. So when I'm saying 1r here, I'm talking about 2r from the center. So if the question says 3r above the surface, and we're using this formula, then we need to take it into account from the center. But let's ignore that for now and just say that we have a problem where we want to throw this projectile up into the air, and it's going to reach 3r and then fall back to the surface of the Earth. Well, you might think that we could just do PEG equals KE. In other words, the maximum PEG that it reaches here comes from that initial kinetic energy. But this formula assumes a uniform gravitational field. So we know that the surface gravity right here is 9.8 meters per second squared. But as we travel further and further away, that value starts to drop. So we can't use the PEG turns into KE. And why can't we do that? Because the gravitation, the strength of the gravitational field, or G, the acceleration, is decreasing. So how can we get this changing gravitational field? Well, we can do a very easy derivation, and this simple derivation is going to be used over and over in many multiple choice questions, and it will also be incorporated into many of the free response style problems. So let's say we're looking for the force of gravity, and we're going to do this for the mass of the Earth and the mass of a person. So when the person is standing on the surface, they are 1 radii away. Well, we can replace this Fg with mg because that's the force of gravity on the person. So that's going to be mp. So that's going to be g, mass of the Earth, mass of the person, over r squared. And then we have the mass of the person on both sides. That gives us g is equal to g, mass of the, mass of the Earth, divided by r squared. So what is this? That's the strength of the gravitational field. It's also the acceleration. So we have to think of it in both ways. Now, if we put in the mass of the Earth and the radius of the Earth, this value would come out to 9.8 meters per second squared. But because we know that if we go further away from the Earth, then these values aren't going to change. So the only thing that's affecting g is going to be r, and r is squared. So let's take a situation where we have the Earth, and we're on the surface here, and we have a certain value. It could be any value, 100, let's say, 100 newtons. Then if we go to 1 radii above the surface, that's 2 radii from the center. So that becomes g equals gm over, and what have we changed? We have changed this by double. We have done that. However, we're squaring everything. So that means if we've divided this by 2 and the 2 is squared, we've cut our g by a quarter. So at this point, this person or object or whatever the thing is would have a weight value or a force of gravity on it of only 25 newtons. And if we continued out, so we would have 9.8 divided by 4, and that would be at 2r. Then at 3r, that would be 9.8 divided by 9. And at 4r, that would be 9.8 divided by 16, and so on. Again, I want to stress that this 2r is from the center, not from the surface. And the way they like to make these questions tricky is to give you the distance from the center, or give you the distance from the surface, and then you have to take into account that it's from the center. This is really fascinating. If we have the Earth, we know that on the surface, the acceleration due to gravity, the strength of the gravitational field is 9.8 meters per second squared. But what if we kept this position constant? So we said that is a location in space, and then we shrunk the Earth. Okay, so the Earth is going to become much more dense, but we're going to say that the mass is exactly the same. So when we look at this formula, G equals gm over r squared, G is obviously a constant. We're saying that the mass of the Earth is going to stay the same, and we're going to leave this position r to be the same as what it was before. So as the Earth starts to shrink and reaches a much smaller size, the acceleration due to gravity at this point is still 9.8 meters per second squared. So we can say that the gravitational effect outside any spherically symmetric mass, outside meaning if we go inside the planet, then things change. Outside any spherically symmetric mass distribution, meaning the mass is evenly distributed through the planet, it's the same as if all of the mass was concentrated in the center. So we can look and say that if we have the sun, and the Earth was orbiting the sun, and the sun collapsed into a black hole. So the sun's mass is not enough for that to happen, but let's just say that it did. Then all of the mass would be concentrated at this one single point that would be at the center of mass of the sun right there. Well, the Earth would not then fall into the black hole. The Earth would continue to rotate around the black hole with the same acceleration that it had at the time that it was out here. Now remember, and this is another important point, that this value G that we've been talking about, the strength of the gravitational field, that is equal to the centripetal acceleration for the planet that's orbiting the sun, or whatever the satellite is that's orbiting the object. Some other things that you should know are about 9.8 meters per second squared, because that number is clearly rounded off. So when we look at the Earth is not a perfect sphere. Now, I exaggerated this a lot, but if we have the North Pole here and the South Pole here, and this is the equator, the Earth is stretched out. The technical term is an oblate spheroid, which means that if you stand on the North or the South Pole, you're actually closer to the center of mass. So that means that the gravitational force of attraction is much, much higher. So in the Arctic, they actually measured this to be 9.8337 meters per second squared at sea level. So somewhere close to the North Pole, but not quite. There is a mountain in Peru, which is pretty close to the equator, and they measured the gravity there. Now, keep in mind, it's not just that at the equator you're further from the center, but they were also standing on top of a mountain, which makes it even further, and that was 9.67639 meters per second squared. So these gravity values are quite different. The value that is often accepted is the value at 45 degrees at sea level. And that value is 9.80665 meters per second squared. But usually most textbooks will say 9.8, and you'll see some use 9.81 because it's a little closer to the truth. All right. So let's go ahead and look at how the force of gravity changes as we move further away from the surface of the Earth. So we're going to call the surface of the Earth 1r, 1 radii. And we'll say that at 1 radii we have a value of 1. Now, I'm going to use pounds for this so you have a better sense rather than newtons. Let's say that we have a person that weighs 200 pounds when they're standing on the surface of the Earth. Well, if we go to 2r, we know that our formula G equals gm over r squared. We have doubled r, so our value becomes 1/4. So a person standing at this point would only weigh 50 pounds. Again, like sometimes they'll ask this question like you're standing on a tall ladder or something like that. If we go to 3r, that becomes 1/9. And 1/9 is 22.2 pounds. Again, 1/9 because it's 1 over r squared. It's 1 over 3 squared. And if we go out to 4, that becomes 1/16, which is 12.5 pounds. Now you can see that this is getting closer and closer to 0, but it's asymptotic because this will always be some number divided by this constant. So we'll always have a g, even though that g approaches 0. So if we graph this, we end up with an inverse square law, something like that. Okay, so that makes sense. But what happens if you dig a hole and go into the Earth? Well, the math on that's actually quite complicated, but the result is very simple. The gravity is linear. In other words, if you go halfway into the Earth, then the gravity decreases by half. So a hole dug halfway into the Earth, which would be here, the gravity would be 4.9 meters per second squared. And at the center of the Earth, if you think of a person, all of the mass in the Earth is pulling in opposite directions, meaning that the force of gravity decreases to 0. So where are some actual practical applications of this? Well, not practical, but some cool things that you can think about. What if you drilled a hole through the Earth and then you jumped in that hole? So if you jumped in that hole, your initial acceleration would be 9.8 meters per second squared, and you would begin to speed up. But the rate that you begun to speed up would decrease. So you'd be going faster and faster and faster, but at a slower and slower rate. Why? Because the acceleration is decreasing. At this point, the acceleration would switch to the opposite direction, and you would slow down until you came out the other side at exactly the speed that you jumped in at. We could say at 0. So what would a velocity graph look like for that? Well, you would increase your speed, but at a decreasing rate. So the graph would look like this, and that would be for velocity and time. What would the acceleration look like? Well, the acceleration would decrease and then increase in the opposite direction. That's with respect to time. It's possible to have two stars that rotate around each other, and this is called a binary star system. You could even have two planets rotating around each other. This is supposed to be a circle, not an ellipse. I didn't draw it perfectly. But they would rotate around their center of mass. And this goes back to the center of mass unit, where we actually did this for the Earth and the Moon, that the Moon does not orbit the Earth. The Moon and Earth orbit the center of mass of the Earth-Moon system. So these two are going to orbit around like that. And if this had more mass, the center of mass would shift over to here. And again, this one would be making a smaller circle. So let me actually do that. But before I do, let me just say that the force of gravity here and the force of gravity here, these would provide the centripetal force around this radius r. So we have to be careful when we deal with these radii, because the distance from mass 1 to mass 2, that's going to be our force that we're going to use in the Fg formula. But when we use AC equals v squared over r, that's going to be the distance from the mass to the point that it's rotating around. So that r would be half of that value of r right there. Now, if we made this mass more massive, then this center of mass would move over to here, and this mass would be making a circle around it like this, while this mass would be making a much larger circle around this. So both are going to be rotating, and you can see it's going to be like that, around the center of mass of the system. So I've seen this question come up before. It sounds difficult, but it's actually not that bad. Let's say we have a trinary star system. So we have three masses and they're all rotating. Well, where are they going to rotate? They're going to rotate around the center of the mass of the system, which is probably going to be there in the center of mass unit. We showed how to calculate that. And the question is, what's the force of gravity on this smaller star? Well, think about it. We have a force in this direction due to the attraction between M1 and M2, and we have a force of attraction between M1 and M3 that's going to be less here. So we can call that, we'll call that force 2, and we'll call this force 1. And what is the actual resultant force of this? Well, it's going to be somewhere out here like this. So if we did this as vectors, we would have our force 1 like this. And how would we get that? Well, we would do G m1 m2 over r squared. The r would be the r between the first two stars, and the masses would be the first two star masses. And then we would do the same exact calculation again for the second star. And again, we would do Fg equals G m1 m2 over r squared, except this time that r would be the distance from here to here, and the masses would be this mass and this mass. If we know R1 and R2, we can find that angle theta, and then we could use that angle theta to break this force into two forces. So if we call this force 2, then we would have force 2y, and we would have force 1 is still there, and then we would have force 2x. And all we would have to do is add those two forces to make a resultant force, and we would have this F2y in this direction. So we have our F2y, this would be our F2x plus F1, and then we could use Pythagorean theorem to solve for the resultant, and if they wanted the angle, we could just do sine, cosine, or tangent. We've seen this before, but I continue to stress it because this, for whatever reason, ends up being the most popular formula that they use for questions in the multiple choice for the AP. So we start out with this formula. We already did this. We put in mg, cancel out the masses. So if we're dealing with a planet and we want to know the gravity on the surface of that planet, we can just plug in some numbers here. So here are some numbers for the Earth. This is the radius of the Earth and the mass of the Earth. And you can do this if you want. You can plug in the numbers. But you would expect that this comes out to 9.8 meters per second squared, which it does. I mean, all sorts of pencil troubles here. And if you do this for Jupiter, you would think the value would be much higher based on the fact that the mass is so much more, but it is much less dense. So it's definitely higher, but it's not as much higher as you might expect. And if you do this for the moon, you get a value of 1.6 meters per second squared. And I'm just showing this to you so that you can see where these numbers come from if they give you a question like this, and also to get a sense that in general, unless the planet has a much different density, the larger the planet, the more massive the planet, the higher the gravitational field is going to be. I just want to say one other thing, which is when you're using this formula or you're using this formula, it's much safer on your calculator to, rather than put something in as, let's say, 5 times 10, and then to do the power, to do that as 5 times 10 caret 2 to square that, it's much better to do 5 second exponent 2. And what that exponent key does is it says 5 times 10 to the 2, and it glues this number together, so it treats this as one number. When you put this in as 5 times 10 caret 2, what you're saying is you're multiplying it, and these are separate numbers. So just a tip to decrease the chance that you're going to make a mistake in case you don't put parentheses or you don't do your order of operations correctly. The exponent key is very valuable, and that's the best way to do it. Okay, so what about this question? This comes up every once in a while. And let's say you have the Earth and you have the International Space Station. Well, when we think of the International Space Station, we think of this thing that's up there in space orbiting around the Earth, and we think of it as being very, very high up. But the International Space Station and all of the satellites that are orbiting are only in the hundreds of miles above the surface. So for the International Space Station, it's only 250 miles above the surface, roughly. That's 410 kilometers. So how strong is the gravity on the International Space Station from this distance? Well, we can do G equals G m of the Earth over r squared. But think about what this r is. That's r from the center. Well, that's going to be the radius of the Earth plus the distance of the height of the satellite above the surface. So that's 638. 0, 0, 0, 0, and 410 kilometers, that's going to be 410,000. So that's 410, 1, 2, 3. Put some commas in there. And that's going to be the height of the satellite. So that our R value that we need to put in the formula is 6,790,000 meters. And when you put that number in, you get a G value of 8.6 meters per second squared. So the astronauts that are in the International Space Station are getting a gravitational field, a force on them that's pretty close to the surface of the Earth. It's not that much lower. So why is it that we say that they're weightless? Well, they're weightless in the same sense that if you jump off of the surface of the Earth, you're weightless while you're falling. And the International Space Station astronauts are falling around the Earth. So their gravitational field is actually pretty close to the surface of the Earth. It just happens to be that they don't weigh anything while they're falling. Okay, let's go ahead and look at this very interesting problem. We have the Earth, we have the Moon that's orbiting around the Earth, and the distance from the center of the Earth to the center of the Moon is about 60 Earth radii. So if we know that, we can figure out the gravity at the Moon. We can figure out the acceleration due to gravity at this point. So all we have to do to find G at the Moon is to put in G, which would be our universal gravitational constant, the mass of the Earth, and divide that by 60 r squared. Now remember that squared is also acting on the 60, and if you do this, G is basically just 9.8 divided by 60 squared. And if you do that, you get G is equal to 0.0027 meters per second squared. Now, what is that? That is the strength of the gravitational field where? At the Moon. So that's how strong gravity, the force of gravity, or I should say the acceleration due to gravity, is pulling in this direction. But remember that that acceleration is also the same as the centripetal acceleration of the Moon around the Earth. So Newton actually did this. Newton did this and figured out the number 0.0027 meters per second squared, which is interesting because we can do this a different way. We can go with method 2, where we could say AC of the Moon is equal to v squared over r. Now, we know that we can also say the velocity of the Moon is going to be equal to x over t, the distance that it travels. Well, how far does it go in one orbit? Well, it's pretty much a circle, so we can say it's the circumference, or 2 pi r. And when we talk about the time for one revolution, then we call that the period, capital T. So the period of the moon is 27.3 days, and you can convert that to seconds, which is 2.36 times 10 to the 6th, but I'm going to do this without numbers. So now we can say AC is equal to V squared. Well, what's V? That's 2 pi r over T all squared over r. Well, that comes out to be 4 pi squared r squared over, bringing this T down, T squared r. One of our r's will cancel, and we're left with 4 pi squared r over T. Now, we know the distance, 60 Earth radii, and we know the time, that's a month, which is 27.3 days, or 2.36 times 10 to the 6 seconds. So what we've shown is that the centripetal acceleration is 0.0027 meters per second squared. So Newton did this. Newton found this value from essentially from Fg equals g m1 m2 over r squared. Then he did this using the kinematics of centripetal acceleration. And what he then concluded was that because these values are the same, then he's saying that the force of gravity doesn't just work on the surface of the Earth, it also works for other bodies in the universe. So what was the whole thing with Newton's apple? Newton didn't tell us that apples fall because of gravity. What Newton really said was that the force that makes an apple fall to the earth is the same force that makes the moon go in its orbit. And that was a huge change in thinking, especially when you consider at the time that people didn't believe that the laws on the earth were the same as the laws elsewhere in the universe. The last thing we'll talk about, I've never seen this come up as a question on an AP exam, but I do think it's important to know this idea, which is this guy Cavendish in 1797 was the first person to come up with a value for big G. And the way that he did this was he took a torsion wire. So at that time, it was very well understood that you could get the force from the twisting of a wire, and you could figure out how much force that was. So then he connected some kind of lightweight beam with two masses on the other side. And then when he moved these other masses, which he had over here, he could move these masses in. Then these two masses would attract to the larger masses, and the torsion, he could get the force by figuring out the angle. And what he did then was to be able to get a value for big G. Big G, to this day, is the least accurately known universal constant of all the different constants that we have in physics.